I'm sure a lot of you remember that in order to add or subtract fractions when the denominators don't match, you have to make the denominators match. But you may not understand why. And the reason that they have to match is because, well, let's think about Legos. Okay, and you have, you have your Legos that are little rectangles with 2 pieces up there. And you have some Legos that are square that have 4. And you have some that have 6.
Don't forget stepping on them really hurts.
Yes. Okay, now, if I call this Lego a half, and this Lego a fourth, and this Lego a sixth. And I want to figure out, okay, so I'm basing this on the number of whatever you call the top of a Lego, the little round bits. I'm sure they have a technical name. I have no idea what it is. If I want to add up a bunch of Legos and give them a value based on how many Legos I have, and account also for the number of the little round bits, and I can add this up and say, okay, I have 1, 2, 3 Legos, but that doesn't account for how many little round things there are. So I have to put these in some sort of common ground to do both at the same time, count the number of Legos and account for the little round things on top. And that's why fractions have to have the same denominator. It's the same size pieces that way. Okay, so if I have, this is 1/2, if 2 dots or 2 little round things represents 1/2, I have 2 of those here. And I have 3 of those here. So I'm going to account for this. I need a common denominator between 2 and 4 and 12, or 6, which is not, 2 and 4 both go into 8, but 6 does not, so I have to keep going, so it's going to be 12. If I make this denominator 12, in order to do that, I multiply it by 6. So I also have to multiply the numerator by 6. So that's going to be 6 twelfths. To make this denominator 12, I multiply by 3. So that'll be 3 twelfths. And to make this denominator 12, I multiply by 2. So this will be 2 twelfths. Now I can add this up. And I have 6 plus 3, 9 plus 12, that's going to be, or plus 2, that's 11 twelfths. This accounts for the number of Legos I have and also the number of little round things on top. So in order to add or subtract rational numbers with unlike denominators, our first step is to give them a like denominator. So we have to find the common denominator. And convert the fractions. Then we can add the numerators. And I say new numerators. We just did this denominator. What's our common denominator between 4 and 6?
12.
And what do we multiply by here? 3. And this one we multiply by 2. So I get 3 twelfths and 2 twelfths, giving me 5 twelfths. Now at this point, if possible, we would reduce. We can't reduce 5 and 12, so we're good. When you add and subtract the fractions, they're going to act just like, yeah, sorry. They're going to act just like integers. So you can get negative answers as well. So keep that in mind. If you get a negative answer, that doesn't mean it's wrong. You can have a negative fraction. For example, I owe you 3/4 of a dollar, negative 3/4. Everybody got it?
Yes.
Okay. All right, so 3 and 7, what's my common denominator? 21, yeah. So I would multiply a 3 times 7 and a 2 times 7, and I would multiply 7 times 3 and a 4 times 3. Now, if you notice, I'm multiplying by the other denominator. That may not always give you the smallest common denominator. In this case, it does. But that will always work. So if you can't think of or find a common denominator that's smaller, you can always multiply each fraction by the other denominator. Just to save you time if you're not finding something smaller. So this will give me 14 21st and 12 21st, which will give me 26 over 21 divides by 2, divides by 3 and 7. They won't reduce. You do not have to convert these to mixed numbers. Improper fractions are perfectly lovely. You leave it just the way it is. Don't make extra work for yourself. Okay. On this one I did, yeah. You wouldn't always, for example, on the, I'd say 3 times 3 is 3. Correct me. Because I know you guys know 3 times 3 is not 3. Right? Okay. Who everybody know that? Yeah, okay. Sorry, that's 11. Sorry. Okay. If I did this though, where I'm using the larger denominator, that's okay, but I'm going to have to reduce. And those will both divide by 2. Which gives you the same answer exactly. Okay, common denominator between 5 and 12. What's my numerator here? What? Yeah, because I'm going to multiply by 12. And my numerator here? 35, because I'm multiplying by 5. 36 and 35 will give me 71 over 60. 71 is prime, so nothing's going to reduce with that at all. And again, improper fraction are okay. Right. Subtracting 6, 7, and 9 common denominator. 63. So it's 26 over 63. Does that reduce? Remember the divisibilities? Add those together and you get 8. So this won't divide by 3. It will divide by 2, but this one won't. So you're good. You can't divide. You can't reduce it. 9 and 3. 9. Do I have to multiply this one by anything?
No.
But I multiply this one by 3. Five ninths minus 6 ninths is going to give me negative 1 ninth. Okay, so 5 minus 6, negative 1. The denominator doesn't get the negative.
Why didn't the 3 get multiplied at
Because it's already 9.
Here, this is already 9, so I didn't have to multiply it by anything. I didn't change it. Now I could have done this one by 9 and this one by 3 and then reduced. But since 3 goes into 9, I can just turn this one into ninths and have less work. When you talk about negative fractions, there's two ways you can write them. You can write the negative in front like that, or you can write the negative on top like that. We don't ever leave negatives in the denominator. It's just not done. Improper, sort of like you wouldn't walk around with a wig on your foot. This is like the wig. You don't put it on the foot. If we add fractions, but let's say I add a negative and a positive, we follow the same rules as the integers. So it'll be negative 6 plus 3.
It'll be negative 3.
Negative 3.
Over 7.
Yeah. So just remember the fractions follow the same rules as the integers. The difference is that the denominators have to match. That's, integers have no denominator. Fractions, the denominators match. But when you add and subtract the numerators, same rules. Also with multiplying and dividing, if I multiply two negative fractions, I get a positive. If I divide two negatives, I get a positive. If I divide or multiply one negative, one positive, I'm going to still get a negative. Okay. When we talk about the density of something, you guys took science, you're familiar with density is how concentrated or how thick something is. Numbers are infinitely dense. Rational numbers are infinitely dense because if I have a number line and I have a half and I have 3/4, I can find a number halfway between these. This is 2/4, that's 3/4. Halfway between 2 and 3 is 1.5/4. We don't say 1.5/4, or sorry, 2.5/4. We do 8ths. This would be 6/8, and that would be 4/8. So this is going to be 5/8. And then I can find another number halfway between 1/2 and 5/8. I'm going to have to go to 16ths. 10/16, 8/16. So I get 9/16. And I can find a number halfway between there, and halfway between there, and halfway between there, etc., and etc., etc. I can keep taking half over and over and over again. It will never stop. It will get beyond microscopically tiny, but it never stops. And this is what we call the density of rational numbers. And there's a good explanation for that on YouTube, actually. Did I show it to you guys already?
Yes. And then she twists it.
Oh, okay. All right, problem solving. No, you don't have to. This is the most likely scenario when you will use fractions for problem solving. Recipes. Recipes are always a half of this, cup of that, and 3/4 a cup of this, or half a teaspoon of that, right?
Yes.
And then they say serve 6, and you say, well, but I need to serve 18, or but I only need to serve 2. So you have to convert the recipe to make the right amount of food so that you're not wasting, or so that you have enough. So here you might want to write this. So if you take the amount of the ingredient needed, that is equal to the desired serving size divided by the recipe serving size. So this is how many you want. Divided by how many it makes. And then you time that by the ingredient amount in the recipe. So if I want 10 servings and the recipe makes 6, I put 10 over 6, and then I multiply that by a cup, or 3/4 of a cup, or whatever the recipe said originally. So this is the formula for that. Cookies. I'm going to make, says 5 dozen cookies requires 3/4 cups of sugar, but I don't want 5 dozen cookies. I want 8 dozen cookies, because 5 dozen cookies is just not enough cookies. So how much sugar would I need? Okay, we'll go back to this, and it's what we want over what it makes. So I'm just gonna, and we want to multiply that times the amount in the recipe. We want 8 dozen. It makes 5 dozen. And that's 3/4 of a cup of sugar. So I'm going to multiply 8/5 times 3/4. And I can either reduce first and then multiply, or multiply then reduce first. Which would you guys prefer I do? Reduce first? Okay. 4 divides by 4 and 8 divides by 4, so those cross cancel. So I get 2 times 3, which is 6. 5 times 1 is 5. So 6/5 of a cup. So this is 1 1/5 cups of sugar. We're going to define what makes an irrational number. We're going to simplify square roots, both perfect and non-perfect. We're going to perform operations with square roots. Operations being add, subtracting, multiplying, dividing. And then I'm going to teach you how to rationalize the denominator. You can't have square roots in the denominator. So I'm going to teach you how to get the square roots out of the denominator. Our irrational numbers. An irrational number is a decimal that never ends and never repeats. So, you know, when we had like 0.3 with the bar over and it's just 3's forever, that's repeating. And it doesn't have to be the same number that repeats all the time. It can be any kind of a repeating pattern. So it could say even 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 5. That's a pattern. Irrational numbers have no pattern in the decimal. Okay. And then they never end. So common example, most famous irrational number is pi. And you guys have all heard that pi never ends and pi never repeats, and there's not a pattern in pi. People have looked for it for hundreds of years. Never found one, because you can't, because it doesn't exist. They've got supercomputers working on it. It's not there. It's a waste of computing power. We round pi and we say 3.14, but that's rounded. Okay. There are other famous irrational numbers. The square root of 2, for some reason, is a famous irrational number. I don't know why the square root of 2 particularly is a famous irrational number, because the square root of 3 is also irrational, as is 5, as is 7, as is any non-perfect square. So for some reason 2 just seems to be like the poster child for, maybe, no, yeah, it won't be the only even irrational square. It's the only even prime.
So irrational numbers are
Non-ending, non-terminating decimals and non-perfect squares will give you those. Now, some perfect squares are decimals. Okay, so the way you tell is if you plug it into your calculator. So if I plug 2 into my calculator and I take the square root of it, takes up all of the digit spaces in my calculator. If it fills up the whole thing, chances are it's not ending. It's just your calculator doesn't have lines and lines and lines of text. It just stops. Whereas if you plug in something and you get like a decimal answer that's like 1.256, very short, that's your perfect square, 1.256 or something. You know what I mean? So if it's a short ending decimal, it's not irrational. If it takes up the whole line of code or text on your calculator and it fills the whole thing up, it's irrational. Because the calculator is just dropping off all the other digits and rounding it. So never ends, never repeats. That's why they're irrational. Okay, square roots can be perfect or non-perfect. Here's the technical definition of a square root. This is the principal square root. We have, every perfect square has two square roots. It has the principal square root, which is the positive, and then the non-principal, which is the negative. And the reason I say that is because if I take 2 times 2, I get 4. That means the square root of 4 is 2. But if I take -2 times -2, I also get 4. 2 is the principal square root. -2 is the non-principal square root. When we're talking about square roots right now, we're going to be talking about the principal square roots.
Be like plus and minus.
Yeah, we're just always going to use the positives. That's the accepted use for square roots, unless you're solving algebraic equations, is you just take into account the positive. Okay. So, oh, what did I do there? Okay. Sorry, let's go back there. Okay, so we have the square root of 36 is 6, because 6 times 6 is 36. And the square root of 36 is irrational. It's rational because it gives us a terminating number. It ends at the decimal point. Okay. So we know not all square roots are irrational. Just some, most, probably even, square roots are irrational, but not all. Perfect squares are rational. Not perfect squares are irrational. Is a number that is the square of a whole number. Oops, that's not what I meant to do at all. All right, perfect squares. You guys know a lot of these. Square root of 1 is 1. Square root of 36 we just did is 6. Square root of 25 is 5. Square root of 225 is 15. 169 is 13. Okay. And I'm giving you the principal square roots on all of these. If I throw in the -2, it's both, but this is the principal square root, the main one. Did we already do a list of squares? No, okay. These are all your perfect squares up through 20, including 25, because it shows up a lot. And then 30 squared is 900, 40 squared is 1600, 50 is 2500, 300 squared is 90,000. When you have multiples of 10, you square the number and you double the zeros. So if I said 160 squared, 16 squared is 256. I'm going to double the zeros. Makes it easier. Because then you don't have to worry about the whole number part. You just twice as many zeros. So that's the pattern on multiples of 10. Okay. You will want these. My recommendation is that you memorize at least up to 15 and 20 and 25. Might as well memorize all the way up to 20, but you need to memorize at least up to 15. It will make this take you half the time to do the work on these, if you have those memorized. And also, of course, if 11 squared is 121, the square root of 121 is, if 11 squared is 121, then the square root of 121 is 11. You go backwards and forwards. Squares and square roots are like multiplication and division. They undo each other. Okay, guys, this is important. You need to know this. If A and B are non-negative, okay, they have to be non-negative, because if one's negative, then you get a negative number, and you can't have negative square roots because we're in real numbers. The square root of A times B is equal to the square root of A times the square root of B. And vice versa, the square root of A times the square root of B is equal to the square root of A times B. So you can split square roots, or you can smash them together. Okay? So what do we need that for? When you're simplifying square roots, if I have, let's say, the square root of 3 and the square root of 27. Neither of these are perfect squares. But if I multiply them together, I get the square root of 81. Perfect square, 9. Okay. Going the other way, go the other way for simplifying. If I take the square root of 200, not a perfect square, but if I split it, 100 is a perfect square. So what I end up with is 10 times the square root of 2. I can take the square root of 100, and I leave the square root of 2 hanging around because I can't simplify it any further. So that's what we use this product rule for. We can split or smash square roots together in order to make it so we can simplify them. So the reason we leave this inside, leaving it as the square root of 2 makes it an exact answer. This is 10 times the square root of 2 is a perfect, accurate, 100% exact answer. If I were to plug 2 and take the square root of it into my calculator, I get a rounded decimal. If I do 10 times that decimal, I'm getting an estimate. Because the square root of 2 never ends, so I can never know the exact answer if I actually try to work with the decimal. So this is an exact answer. Anything else would be a round or an estimate. So we leave it alone and we say that's the perfectly perfect, exact, 100% accurate answer. Okay, so simplifying square roots. 75, not a perfect square. Now there's two ways you can do this. In the first method, you might recognize that 75 is 3 times 25 and that 25 is perfect square. And the square root of 25 is 5. And the square root of 3 we leave alone. So we pull the perfect square out. But let's say you don't recognize the 25 in there for whatever reason. The other way we can do this is we can factor it. And then you'd say, okay, 3 times 25 and 5 times 5. And if you do a factoring, you factor down to prime factors. when you find these matching pairs, they get to go out. That's just like if you find somebody that matches you, you get to go out on a date. Right? So if you're a couple, you get to go out. If you don't have anybody to partner up with, you stay home. Okay? So when you're factoring these, that's how that would work. Couples go out, lonely guys, girls, whatever, stay home. Okay? So 500, if you recognize the perfect square of 100 in there, take the square root of 100 as 10, the 5 left behind. If you didn't recognize it for whatever reason, and you factor this down, and you say, okay, I have a pair of 5s, and I have a pair of 2s, and I have a 5 left over. The 2s get to go out, the 5 gets to go out, or the 5s get to go out, and this other 5 stays home. Anything that comes out gets multiplied back together. Anything that stays home gets multiplied back together if there's more than one, times square root of 5. Did you get the same answer? I think that's me. Prime, right? So this is already simplified. You don't do anything to it. You just leave it exactly like it is. Okay. I could do something like the square root of 6. 6 isn't prime. It's 2 times 3. But nothing matches. So it's already simplified. I can't take anything out. So it just stays the square root of 6. Okay. They have to have something to match to be able to bring it out. There has to be a perfect square inside to bring it out. Oh, darn it. We're doing that again, apparently. If there are numbers outside of the square root, those get multiplied together. If there are numbers inside, those get multiplied together. And then you simplify if possible. So for example, if I had 3 times the square root of 4, no, not 4, 4 is a perfect square, 6 times 5 times the square root of 3. Okay. The 3 and the 5 are going to get multiplied together. That gives me a 15. The 6 and the 3 are going to get multiplied together. That gives me an 18. Okay, so what I'm basically doing is I'm going from here to 5 times 3 and, or sorry, 3 times 5. I want to write them in order so they're not confusing. Like that. Okay, so multiply the numbers outside, multiply the numbers inside. Simplify if possible. Well, 18 is 2 times 9, and 9 is 3 times 3. That's a pair of 3s. So a 3 can come out. The 15 is still there. It doesn't go away. The 3 comes out. The 2 remains behind because it's alone. And then 15 times 3 is 45. Square root of 2 times the square root of 5, square root of 10. 10 is just 2 times 5, nothing matches, so I can't simplify it. Square root of 7 times the square root of 7, which is 7. If you have this situation where they match, you can skip this step and go straight from here to here. Squaring a square root cancels it out. And squaring is when I remultiply something by itself. So the square root of 7 times the square root of 7, that's the square root of 7 squared. So if they match, just take the square root away. You can skip this step if you want to. You don't have to though. Square root of 6 times the square root of 12. 72. Two methods. We have 8 times 9. 9 is perfect square. Oops, 8. Or you can factor it. And you don't even have to factor it all the way. Once I got here, if I did that, I know that there's a pair. Hold on, dude. 8 will still reduce further. It's got a perfect square in it. That's where I messed up. So the 2 comes out. I get 6 times the square root of 2. Same as I would get here with that pair. And the 2 stays home. I'm glad that I did that. Be careful of that. I saw the 9 and went, oh yeah, perfect square, I'm done. But the 9 wasn't the only perfect square in there. 8 had a 4 hiding it, which was also a perfect square. So if you do this method, just be sure that whatever number you leave behind, just double check yourself and make sure there's no perfect squares hiding. When you factor, they all show up, so they can't hide. So just be careful if you do this one. Remember, quotient's the answer you get from dividing, so there's a quotient rule for, okay, A and B, non-negative, B can't be 0, and the reason B can't be 0 is because we're going to put B in the denominator, and you cannot divide by 0. So, just like with multiplication, if you have 2 separate square roots, you can mash them together and make it a square root of a fraction, because maybe that's reducible or something. Or if you have a fraction, you can take it apart and make it 2 separate square roots. Now, this method you will use if reducing the fraction gets you a perfect square. Because we don't leave fractions under square roots, and we don't leave square roots in the denominator, which we'll talk about in the next part where we talk about rationalizing the denominator. No, okay. So everybody got that? You don't have to write all the words, but you want this part at least. And that part, that B can't be negative. Square root of 49 over 81. Square root of 49 over the square root of 81. 7 over 9. Sometimes the fraction is reducible, but reducing doesn't do much for you. For example, if I had 36 over let me flip that. 16 over 36. These are both even, so I could reduce it, and that would give me 8 over 18, which would give you, yeah. But, yeah, you could do, you get 4 over 9. I guess that would still work. But you could take the square root of the 16 and the square root of the 36, and you get 4 over 6, which gives you 1/3. Mm-hmm. 2/3, not 1/3. Here, not perfect square, but if I put them together, 75 divides by 3, I get 25 perfect square. 90 over the square root of 2 doesn't perfect square. Square root of 90 over 2 gives me the square root of 45. Not a perfect square, but simplifiable. Okay. So when you see this, before you do the next thing that we're going to do, which is rationalize the denominator, see if it will simplify it down first. Like if the numerator is divisible by the denominator and you can make it into a non-fraction that way. This is very similar to adding and subtracting like terms, x's and y's. So you want to treat the square roots like a variable. And if I have 2x plus 3y, can I do anything with it? Okay, the answer is no, because they don't match. It's just 2x's and 3y's, and I can't do anything with it. But if I have 2x's and 3x's, I can put them together. So because these act like square roots, we treat that, or act like variables, we treat them like variables. Square roots with the same radicand, that's the number under the square root sign, the radicand. Yeah. Can be added or subtracting by adding and subtracting their coefficients. So if I have 3 times the square root of 2 plus 5 times the square root of 2, these match, so I can add them together. So what that equals is 3 plus 5 times the square root of 2, or 8 times the square root of 2. If I have 3 times the square root of 2 plus 5 times the square root of 3, these don't match, so you can't add them. Okay, the square roots have to match.